I welcome you again to the class. Okay, welcome back to the class. As far as the topics from now are concerned, the topics which we are going to start from now onwards, we'll be starting the theories of failure. Okay, we have to talk about the theories of failure. They are very important theories for an engineering student. Theories of failure are to be understood by the students who are dealing with mechanical engineering or who are dealing with civil engineering courses. What are theories of failure? As far as failure is concerned, theories of failure are concerned, we often know that the structural components or the machine elements, they do fail. And in our day-to-day life, we see things failing. Like we have seen bridges collapsing, we have seen the axle of the car breaking. We often see cars, or we say automobiles, stuck on the roads with their axles or shafts broken. We often see houses collapsing and many other structural elements or machine components failing. The gears do break, the bearings give up, and many machine elements do fail, and there's no substitute to the failure. Failures do happen. As engineers, a student who is dealing with, who is studying mechanical engineering or who is studying what we call as civil engineering should be fully acquainted with the concept why and how things fail. Why do things fail? Or how do they fail? What are the conditions under which the things fail? It should be well clear in the mind of an engineering student. As far as the basic mechanics of materials is concerned, the basic mechanics of materials does give us the introduction to understand the failure of things, to understand how machine components fail, and how as machine designers or the students of mechanics of solids, we should select the dimensions of the machine components so that they do not fail. So we are having lots of theories of failure. We are having maximum shear stress theory. We are having octahedral or distortion energy theory. We are having Coulomb's Mohr theory and many other theories which we'll be studying under this heading. But important is understanding the failure of things. In the coming semesters, the students are taught the courses like machine design. As far as machine design is concerned, why do we design things? That's the question. We design things so that they do not fail. For example, you take an example of a cycle, bicycle. If two persons are on a bicycle, one is riding and another one is on the carrier of the bicycle or on the front axle of the bicycle, okay, the supporting axle of the bicycle, the frame axle of the bicycle, you will see that the bicycle does not fail. The frame does not bend, the tires or the rims do not bend. The cycle works as per the expectations. But there are cases, if four persons ride the bicycle, if say for example five persons, then there are chances, and it does happen, that the tires give up, the axle gives up, the pedal gives up, okay. So the frame starts bending, so on and so forth. So there is a limitation. There are some elements that define whether a machine component will fail under the given conditions or not. So understanding the failure of things is very important, because without understanding the theories of failure, this student can neither design any machine component nor can predict its proper functioning. So before we go into the theories of failure, we should first and foremost understand why things fail. The basic and the fundamental theory in the mechanics of materials is that every machine element can withstand a maximum amount of stress. That is what we call as the ultimate stress, which we have already discussed in the class. We have conducted tensile test, and we have calculated the maximum amount of stress a machine element can withstand. That's what we call as the ultimate stress. Ultimate stress is the stress where actually the breakage of the machine element was happening. The failure was starting. The necking happened at the ultimate stress. Now let's suppose I have a machine element. Let's suppose we have a machine element, and this machine element, the area of cross section of this machine element is, say for example, A, and let's suppose its length is L, and this machine element is made of an alloy of steel. It's made of steel. We call that as, it's made of, say for example, steel 1. Its carbon content, chromium content is all given to us. Okay, now what happens, this steel, it is given to us, lots of tensile tests have been performed on this, and it is given to us that if a normal stress of, say for example, 400 megapascal is applied, we have performed the tensile test of this machine element. Let's suppose we have performed tensile test of this machine element, cylindrical rod, and during tensile test we have noted that if we apply a stress of 400 megapascals, then this machine element breaks into two. Okay, then this machine element breaks into two. So the maximum stress that this machine element, maximum normal stress that this machine element can withstand is equal to 400 megapascal. Okay, now the question is, let's suppose that this machine element is subjected to load P, which is a normal load, acts along its longitudinal axis. Therefore, the normal stress created, by this load will be equal to P by A. This is the normal stress created. Okay, and this normal stress should be less than 400 megapascal for this machine element not to fail. Okay, so who is giving us the information that this machine element can withstand a load of only 400 megapascal? It's an experiment, it's a test, and for us it's a tensile test. So with the help of an experiment, with the help of tensile test, we are in a position to understand that this machine element is going to fail only when we apply a load of 400 megapascal. So whatever load you are applying actually to this machine element, practically to the machine element, when this machine element is in use, the stress created should always be less than 400 megapascal. Okay, in other words, we say if sigma, the normal stress created by load P, is greater than 400 megapascal, okay, if this stress is greater than 400 megapascal, then this machine element will break into two and we say it fails. So this becomes a failure criterion for us. For this machine element, we say this is a failure criteria. The failure criteria says that this machine element is going to fail if you apply a stress greater than 400 megapascal. So it means that as far as the criteria of failure is concerned, the criteria of failure it comes from the stress distribution in the machine element. We have to see how much stress it can withstand experimentally, and then that experimental value of the stress will give us a criterion for the machine element not to fail. Okay, this is one thing. Number two is so first and foremost, we should remember the criterion is the stress distribution. So we should know how the stress is developed. Number one. Number two is, if I take a machine element like this, if we have a machine element like this, let's suppose we have a cylindrical bar, and this cylindrical bar is fixed at the bottom. Let's suppose it's fixed at the bottom. And this cylindrical bar is subjected to load. Let's suppose the load applied on it is, say for example, P. Let me reverse the direction of the load. Let's suppose the force applied is force F. We're applying force F on this machine element. Okay. The area of cross section of this machine element is, say for example, A. Okay. Therefore, we can say on this plane, Let me draw the plane clearly. On this plane, on the normal plane, on this plane is the normal plane. The normal stress applied will be equal to sigma, which will be equal to F by A. So we say that this machine element is subjected to a normal force, and the value of normal force is equal, normal stress is equal to F by A. And this normal stress is acting on an area which is perpendicular to the force, and that is this area of cross section. Okay, and this we say this is the normal stress. Now if someone takes, if we take the element, if we take the what you call as um, the section not in this direction, if say for example we take a section, say for example like this, let's take a section like this. If section is taken like this, okay, what is the stress acting on this, what is the stress on this, on this section? Okay, how much is the stress acting on this section from here to here? The stress acting on this section will be equal, let me highlight this, the force acting in this direction, the force is acting in this direction. How much is the stress created by this force F on this area, a green area? Okay, we will say the stress created will be equal force, that is F, divided by area. That area will not be equal to A. We'll call this as A prime. A and A prime are different. The reason is A is this area. A is the area of cross section. And as far as A prime is concerned, A prime is the slanted area. A prime is the slanted area. Okay. Now we can see the question is this F on this green section can be resolved if we say let us take this angle to be angle theta. Let's take this angle to be angle theta. Or let me take the angle. Let's take this angle to be angle theta for simplicity. Let's take this angle to be angle theta. Okay. Or since in most of the books the angle between the two areas is given, let me return back. Let me call this to be angle theta. Okay. This is the angle theta, is the angle between the two planes. Okay, the angle between the two planes is theta. One plane is along this direction, another plane is this theta. Therefore, this angle will be 90 minus theta. This angle will be 90 minus theta. Now this F can be resolved into two components on this green section. We can resolve this F into two components. We can say it has one component along this direction. Okay, and we'll call that as F cos of 90 minus theta. F cos of 90 minus theta. And it has another component in a direction perpendicular to F cos theta, that is this. And we'll call this as, this is equal to F sine of 90 minus theta. This component is F sine of 90 minus theta. Okay. Now, as far as this F cos of 90 minus theta is concerned, F cos of 90 minus theta is acting in a direction parallel to this green area. Okay, I'm repeating. As far as this F cos of 90 minus theta is concerned, this force is acting in a direction parallel to this green section, parallel to this green area. And as far as this F sine 90 minus theta is concerned, it's acting in a direction perpendicular to this section, perpendicular to this green area. Okay. So we are getting an indication that F cos 90 minus theta, which is acting parallel to this section, green section, will create the shear stress. And F sine of 90 minus theta, which is acting perpendicular to this green section, will create the normal stress. So it means on this section, green section, which is at an angle theta with respect to the given section, with respect to the given area of cross section, there will be both normal stresses and shear stresses. So I'm repeating to the students. So as far as the two forces are concerned, the two forces F cos of 90 minus theta is acting parallel to the green section, and F sine 90 minus theta is acting in a direction perpendicular to this green section. So F sine 90 minus theta will create the normal stress, and F cos of 90 minus theta will create the shear stress. So it means, as far as the section is concerned, as far as this green section, the inclined section we'll be calling the green section as the inclined section. As far as the inclined section is concerned, the inclined section is a section which will be subjected to both the normal stress because of F sine 90 minus theta, and because of shear stress because of F cos of 90 minus theta. So we will write on a plane which is at an angle theta with respect to the original area of cross section on this plane, which is at an angle theta, the normal stress that we are writing sigma theta is equal to the normal force, that is F sine of 90 minus theta, F sine of 90 minus theta, divided by the area, that is area of this section, okay, area of this green section, which we are writing as A prime. Okay, we can further write this as, okay, we can write F sine of 90 minus theta. As far as the sine of 90 minus theta is concerned, sine of 90 minus theta, we will use the trigonometric function sine of for sine and cos, and we will also use the formulas for a and a theta. Okay, so as far as sine of 90 minus theta is concerned, that's equal to cos theta. So we'll write this as, this is F sine of 90 minus theta is equal to cos of theta, divided by A prime. A prime is the area of the slanted area. Okay, now as far as A prime is concerned, A prime is the slanted area, green area. This area is the, this area is the, this area is A, this area is, this area is, this area is okay, this area is A prime. Okay, this area is A prime, this is A. Okay, this, so this is A, this is A prime. So this is a right angular triangle for us, this is a right angular triangle, and this angle and this angle are corresponding angles, therefore this angle will also be theta. We can write, as far as cos theta is concerned, we can write cos theta, cos of theta is equal to base by hypotenuse, that is A by A prime. Therefore our A prime will become, A by cos theta. This is the relationship between these two areas. Okay, so we can write this as, this is A prime. A prime can be written as area of cross section divided by cos theta. Okay, that is equal to F by A, that is equal to F by A, and cos theta is equal to cos square theta. Therefore we can write, as far as the stress, normal stress on an inclined plane theta, a plane which is inclined at an angle theta with respect to the original area, okay, is equal, original area of cross section is equal to F by A. As far as F by A is concerned, F by A is equal to sigma. F by A is sigma cos square theta. Okay, so when, this is an important formula, when theta is equal to 0, when theta is equal to 0, whenever theta is equal to 0, then this slanted plane, inclined plane becomes equal to this original plane. Okay, when theta is equal to 0, then sigma theta becomes equal to sigma. At that time the value of sigma theta becomes equal to sigma. This is important. We can also solve this as, let's talk about the shear stresses now. as far as the shear stresses are concerned, we can write as far as the shear stress on this inclined plane is concerned. On inclined plane, the shear stresses are represented by tau, we know it. Therefore, inclined plane will represent by theta. Tau, shear stress on an inclined plane, which is inclined at an angle theta, is equal to the F, the parallel force, F cos of 90 minus theta, divided by the area over which this F cos of 90 minus theta is acting. It's acting over A prime. So we'll write this as A prime. So that is equal to, this can be written as far as cos of 90 minus theta is concerned, we'll write the formula for cos of 90 minus theta. As far as cos of 90 minus theta is concerned, cos of 90 minus theta is equal to sine theta. So this will be F cos of 90 minus theta is sine of theta. This is sine theta, and we know A prime is equal to A by cos theta. That's cos theta will be in multiplication to this. So this can be written as, this is equal, if we multiply and divide both sides by 2, okay, so this will be F by 2A. Then we have 2 sine theta cos theta, that's equal to sine 2 theta. That is equal to sine 2 theta. Therefore, the expression for tau, shear stress on an angle inclined plane at an angle of inclination theta, is equal to F by A is the normal stress, that is sigma by 2 sine 2 theta. So these are two important formulas. As far as the stress distribution is concerned, if we take a plane, so if we recall what we have done, if we take a plane, let me repeat it. If we take a plane, we had a machine element, we can, let me redraw this. We had a machine element like this, okay, and this machine element was subjected to force. It was subjected to force F. So if we take a section, if we take a cross section like this, whose area of this cross section is, say for example A, this is force F, then this force F will create the normal stress, and the value of normal stress will be equal F by A. So we say on this plane, I will call this as plane 1 1 prime. On plane 1 1 prime, there is normal stress, and the normal stress is given by F by A. But if we happen to take a plane, if we take a plane at an angle, at some angle with respect to this plane, let's take a plane, let's take some other plane inclined to this plane. Let's take a plane like this, and we call this plane as plane 2 2 prime, such that the angle between these two planes is theta. Okay, then we have on the plane 2 2 prime, on this plane, on the plane 2 2 prime, there will be both. On this plane there will be shear stress tau, and on this plane there will also be the normal stress that will be calling as sigma. So it means, as far as whether there is a normal stress or a shear stress in a machine element, it depends upon the plane which we have selected. So if we are selecting 1 1 prime as a plane, then on this plane there will only be the normal stresses, because there is only normal force acting on it. But for any other plane which is at an angle theta with respect to this plane, there will be both normal stresses as well as the shear stresses. This is the equation for normal stress. This will be the equation for shear stress. Okay, so this is all for today. Now we have to understand, so it means as the value of the normal stress is concerned, it varies as we change the angle theta. The value of shear stress changes as we change the value of angle theta. So it means as the value of sigma and tau are changing, there will be a particular value of theta at which normal stress will be maximum. There will be a particular value of theta at which shear stress will be maximum. So we should know how much is the maximum shear stress created in the machine element, how much is the maximum normal stress created in the machine element. We'll be discussing that hopefully in the next class. Thank you very much.